So today we are going to start force system, and this is the first lecture on force system. So these are the topics that we are going to cover inshallah in this lecture. So the objective of this lecture are to define what a force is and what are their different types. And then inshallah we will discuss a very important principle that is called principle of transmissibility. And then inshallah we will discuss parallelogram and triangle laws, which we have already discussed in the vector topic, but here with reference to the force, how to find the resultant of two forces using parallelogram and triangle laws. And finally, we will demonstrate through examples how to find rectangular and non-rectangular components of a given force. So what is force? What is, in Arabic you call it quwa. Okay? Ta marbuta, quwa. So, and as you know, this force or quwa, it's a vector quantity. But first question arises, what is the definition of the quwa? Anyone can tell me what is the definition of quwa? What is force?
Anything you make to apply to make a change in position or something.
Uh, yeah, actually, there is no universal definition of quwa. There is no universal definition of force. You can say action of one body on another. For example, this is one my hand, this is another hand. I am applying, so I'm doing action over this another body. So this can be considered as a force. So action of one body on another can be defined as a force. And force specification, because it's a vector quantity, it must have a direction, it must have a magnitude. But apart from this also, you have to also specify the point of application or line of action, depending on what type of body you have. For example, if your body is a soft body, and if your body is a rigid body, in case of soft body, it is the point of application of the load that matters. For example, if you apply the force here, you will see the immediately deformation over here. Okay. But if you have a rigid body and then you apply the force on it, as you know, in case of rigid body, there will be no deformation. No deformation means there will be no strain and there will be no stress. Okay. So in case of rigid body, it is the line of action that matters. So if line of action is different, then the force effect will be different. But if the line of action of the force is same, and anywhere it is acting on the line of action of the force, its effect will be the same. But in case of soft body, it is the point of application that matters, because if you apply the force here, you will see the deformation here. And if you go and apply the force in the same line even over here, it will give different effect. Maybe this part will come out. It will be like this. Okay. So apart from magnitude and direction, this also for soft body you have to also see where the force is acting, and for rigid body, what is the line of action of the force, in which line the force is acting. Okay, because if the force is acting in the same line anywhere on the rigid body, its effect will be the same. So now, what are the effects of a force? When you apply force on a body, what effects it shows? You see, one effect which is called external effect, it is related to the re reactions. irrespective of the type of body, whether you are having the soft body, deformable body, or you have a rigid body. For example, this is a table, and if you apply a force on this table, say 100 Newton, then in order to balance this, force will be generated between the leg and the ground as a reaction. And if this force is symmetrically acting at this just at the center, so these reactions, as you know, it will be equally distributed 25, 25, 25, and 25. So this is called external effect because these reactions are external to the body. So this is called external effect. So whether body is deformable body or body is a rigid body, you will see the external effect always. Okay, in order to balance the force, if the body is not going to have acceleration, it has to be balanced. Then this external effect must have to be produced to balance the force. Another effect is the internal effect. So when you apply force on a body, for example, this is the body, and you're applying the force like this, for example. So you are pressing the body. So because of this pressing, this body will have some compressive deformation. The edges of the body, they will try to come closer. Okay. So, and body may deform if it is a deformable body. And because of this deformation, as you know, deformation will produce the strain. Strain is what? Deformation per unit length, for example, in the linear body. Okay, and then this deformation, this strain will produce a stress. And from the Hooke's law for an elastic body, the stress is proportional to strain, and stress upon strain, it's constant, which is called modulus of elasticity. So this deformation will produce the strain, and strain will produce the stress. So this stress and strain will produce only in deformable body, because for rigid body there will be no deformation. For example, if a piece of stone you have buried and then you apply the force on this piece of stone, eh, some force by your own hand, so no deformation. So no deformation means no strain. No strain means no stress. So internal effect, this is called internal effect. This is stress and strain which is producing inside the body. So internal effect you can see only in case of deformable body. Internal effect you can see only in the deformable body. In rigid body you will not have any internal effect, but external effect you can experience with both bodies, whether it is a deformable bodies or it is a rigid body. So in this course, most of the time we are concerned with rigid bodies. So when you are dealing with the rigid bodies, you don't need to bother about the internal effect. Okay. But of course, there are some topics where we will consider the body as a deformable body, like in the case of trusses, like in case of beams. Okay. So there we will try to find out the internal forces. Because this stress, if you multiply with the cross section area, it converts into the internal force. Okay. So in the case of truss or in case of beam, we will find out also the internal forces. So that is the place where the body will be treated as deformable body. Otherwise, in almost everywhere rest of the course, we will be treating our body as a rigid body. So there will be no internal forces. Now, principle of transmissibility. What is the principle of transmissibility? This principle is applicable only for rigid body. According to this principle, if you have a rigid body and you apply the force anywhere on the line of action of the force, its effect is going to be the same. For example, if this is the body and this is its weight acting down, so you may have the reactions over here, and also you may have the reaction over here. And suppose you are applying the force over at point B. So in order to make the equilibrium at this hinge point, a reaction will develop in this manner, which will be same as this force. Okay. So these are the reactions or external effects which are produced at the supports. Now if you move this force from here to here along its line of action, this is the line of action, and this is no more here. Then again these reactions will be the same. Or if you move this force from here to here, then again the effect will be the same. It means if you move from here to here, the vertical reaction and horizontal reaction all will remain the same. They will not be affected. So this is called principle of transmissibility, and is one of the very useful principle which we utilize a lot in solving the problems. So by the help of this principle, you can move your force for the sake of analysis to a place where it is convenient along its line of action. For example, if this is the body and here is the force acting and here is the force acting, and you want to find out the resultant of these two. So you can move this force along its line of action. You can move this force also along its line of action. So this force will become here. This
Like,
force.
so we're sketching the line.
Yeah, this is the line of action of the force. Okay. So anywhere you can move this force, anywhere you can move this force along its line of action. And now we have moved this over here, moved this over here, and now you can apply the law of parallelogram and get the total force resultant. So this will be the resultant. Okay. So this is by the help of principle of transmissibility. By the help of principle of transmissibility, you can apply the force anywhere along the line of action. The effect will remain the same. But keep in mind, this is only and only true for rigid bodies, not for deformable bodies. Now, types of forces. First type of forces based on how they are applied are two. So there are two types of forces uh, with regard to how they are applied. First type of forces are called contact forces, and second type of forces are called body forces. Contact forces are generated through direct physical contact between two bodies. Like this is my one hand, this is another hand. So this force, this is a contact force because here one body is physically touching the other body to apply the force. Same thing in this picture, that this boy is physically touching the football and applying the force. So this force is a contact force. On the other hand, there are some forces which we apply by remote without touching them. These forces are called body forces. You might have seen in your family or in the malls many times children they play with remote controlled cars. So when there are remote controlled cars, so what they do, they just keep pressing some buttons and car goes forward, backward, move from A to B. Okay, or you have seen remote controlled helicopter. Just you press the buttons and helicopter goes up, comes down, goes forward like that. So these the forces which are applying over the helicopter or the car, that forces are without touching those. So they will be considered as the body force. Same thing with your most of the your car. Nowadays, most of the cars have a remote control. So just by pressing some buttons, you can open the door, you can open the trunk, or even you can start the engine nowadays. Okay. So this the force which you are applying over your car to do some action like opening the door, opening the trunk, or starting the engine, they are also body force. And why we call the body force? Because the force which you are applying, eh, that is acting over the entire body. Okay. Gravitational force is also another example of body force. For example, this is a rocket that is moving from the Earth to the moon. So when the rocket is near to the Earth, then Earth gravitational pull is high and moon gravitational pull is small. So both are the body forces. Both are body forces. And when it reaches near to the moon, moon gravitational force becomes more than the Earth gravitational force. So this is also body force. So anything, even for example, this is one object. If I leave, it will go down. Why? Because the Earth is applying the force on it by remote without touching it. So this force it is applying without touching it. So because of that, it is going down. So this all are body forces. And magnetic force, magnetisi force, all the remote control car, remote controlled helicopter, etc. All they are having basically the magnetic forces. They apply magnetic forces. And by simple magnet also, if you have a magnetis here over a table, for example, and then you keep the pieces of iron. So what you see that they are attracted toward this magnet. So here also magnet is not physically going and touching them, but it is applying the force, and because of that they are coming towards it. So these are also body forces. Okay. So based on whether the forces are physically touching or not touching, we have two types of forces: body force and sorry, we have contact force and body force. Okay. Now this is the real life application of the body force. As you know, in the sea, uh, always tides comes. Yeah, that is the rising of the sea surface. Okay, why it is so? This is because of moon. So when moon is say here, full moon especially when it is here, then what will happen? The water which is over the earth surface, this is pulled toward the moon, and because of that you see this bulging eh, in the water. Okay, so you see some long waves. And on the other hand, if you see the position here or position here, because the because it is not in the direction of the moon, so you don't have the high tides here, but here you have the high tides. Similarly, when the moon will reach over here, then you will find the high tides here and low tides in these two places. Okay, so this tide formation is because of the body force that moon applies over the sun, over the earth uh, surface water. Now, another classification of forces is based on in how much length or area they are acting. So, if forces are acting over a very small length compared to the other dimensions, for example, if this is simply supported beam and your force is just acting here, so this force will be called as concentrated force or point force. And why we call it point force? Because it is acting over a point. Okay. On the other hand, you can have another type of force which is not acting over a point, rather it is acting over a length or area. For example, this is the cement bag you have put over the beam. So this force which is acting here, it is not acting over a point, but it is acting over this much of the length. Okay. So this force we call as distributed force. It is written here distributed force. So this is an example of distributed force and this is example of concentrated force. And this is the notation by which we show the distributed force. It does not mean it is subject to 1, 2, 3, 4, 5. No, this is simply a way to show distributed force that you show the force by arrows close to each other. So this is example of a distributed force. And as I might have said before, this is this concentrated and distributed forces, they are basically relative definitions. They are relative, means there is no force in absolute sense concentrated, there is no force in absolute sense it is distributed. It is same like tall and short, fat and thin, rich and poor. Okay, I like they are relative words, rich and poor. Who is rich, who is poor? Eh? The same person who is rich at one place, he may be poor at the other place. And I give you example, like for example, you may be very rich compared to a person who is cleaning the road. Okay, but you might be very poor compared to Bill Gates. Yeah. So uh, it is relative to whom you are comparing. Same thing here also. A force, a man who is standing over a long bridge. Yeah. So you can say that the force which his legs are applying, that compared to the entire length of the bridge, this is very, very small. So this we can consider as a concentrated force. But if the same man he puts his leg over a concrete block, then of course it is acting over the entire length of the concrete block. So this will be a distributed force. So at one place when he's applying the force over a concrete block, it is a distributed force. But when he's applying the force over a long bridge, it is a concentrated force. Okay, and this is the notation how we show the distributed force. And distributed force magnitude we show by load intensity. Load intensity means like in this much of the length, the total weight which is acting is say 10 kilonewton, and this length is say 2 meter. Okay, it means 10 kilonewton force is acting over 2 meters. So per meter it will be how much? In 2 meter, 10 kilonewton force. In 1 meter it will be 10 into 1 divided by 2, that is 5. So 5 kilonewton per meter. This is called load intensity in case of distributed force. So here we are writing load intensity 10 kilo per meter. Here we are writing as is the force 30 kilonewton. Now adding the two forces with the help of parallelogram law and triangle law. So this already we have discussed that if you have the two forces, say one force is here and another force is here, What is the total force? So we have moved this force along its line of action. We have moved this force along the left side. Where they are meeting, there we can make the parallelogram. So the diagonal will represent the total force. You can do the same thing with the help of a triangle law. You put at the head of the first the tail of the next, okay, and then join the tail of the first to the head of the last. So you will get the total force by triangle law. And this force, they are going to be exactly same. Here, if you want to add two forces which are acting over a body in uh, and they are parallel. For example, if this is a table and you are applying the force here and your friend is also pushing this over here and both forces are parallel. Magnitudes are different, but they are parallel. Like by one hand you are applying, he is applying. Okay. So in this case, if you want to find out the resultant by the help of parallelogram law, you cannot do it directly because when the two sides are parallel, how can you show them as the two sides of a parallelogram? Okay. So when the two forces are parallel, you cannot show these two forces as the two sides of a parallelogram. They must be at certain angle. So in this case, what we are going to do, like here, this is one force, this is another force. This is one force, and this is another force. We want to find out the resultant by parallelogram law. So what you do, you will apply to imaginary force vector F and minus vector F in the same line, so that the total force is zero. So you are not adding anything, in fact. Now apply the law of parallelogram between this and this force and get the vector R1. Here apply this and this and get the vector R2. Now move this force over somewhere they are meeting. Now again draw a parallelogram, draw a line parallel to this, draw a line parallel to this. So this will be vector R. So this one vector R, it will be equals to vector R1 plus R2. How? You see vector R equals to vector R1 plus vector R2. And vector R1 is nothing but this plus this. Vector F1 plus vector F. And vector R2 will be vector minus F plus vector F2. So you will get vector F1 plus vector F minus vector plus F2. So these two will cancel. So you will left with vector F1 plus vector. So even by the common sense, you know that what will the total force here in this case, if this is F1 and this is F2, that will be simply summation of the two because they are parallel. Okay, so you are getting the same thing by parallelogram law also. But we have done it by indirect procedure. Now we come to the components. This also I have already discussed in the vector topic. So if this is the force and these two are its horizontal and vertical components, such that the resultant of these two will be this one by parallelogram because the draw line parallel to the draw line parallel to this. So diagonal will represent the resultant. So suppose this force, let's talk in terms of scalar approach, is making an angle theta here. So this we have discussed that on angle side is always cosine. And this will be f sine theta. Okay. So your fx is f cosine theta and fy is f sine theta. So the total force will be definitely f equals to square root of fx square plus fy square. That means f cosine theta is whole square plus f sine theta whole square. And you can find also the tan theta. this upon this is equals to f sine theta, and this is equals to f cosine theta. So this cancels sine theta over cos theta. So from here you can get theta tan inverse of this value. Okay. So here it is written fy. This is fy over fx. So this upon this magnitude wise. So theta will be equals to tan inverse fy over fx. Okay. And if you want to express in the vector form, so vector f is equal to vector fx plus vector fy, and vector fx is what? F cosine theta into I, because unit vector in the x direction is I. That is fx into I. And vector fy will be nothing but fy into j. So you can also express this in vector form. And this is in the scalar form, how to do the calculation. And when you have the non-rectangular components, so again vector f will be equals to vector f1 plus vector f2. But in this case, the calculation is more. You have to use cosine law and sine law in order to resolve and solve this problem. Now I'm going to solve two problems. One is related to the rectangular components, and another is related to the non-rectangular components. So this is related to the rectangular components. And this is one of the very important problem from concept point of view, because the concept which we are going to discuss in this we are going to use frequently throughout this force system. The force F has a magnitude of 600 Newton. Express F as a vector in terms of the unit vectors I and j. Identify the x and y scalar components of vector F. You see here the first question is convert this force into a vector. Okay. So how we can convert a given force into vector? Yes, Mr. Omar. Yes, please.
Yeah, because of this is rectangular, so we use the sine and cosine.
Yes.
So we say 600 sine 30 for the x component.
Yes,
Or,
600 sin theta
yeah,
for y component. Because in this problem, because this is the angle side, okay, so
no,
this will
sine
be,
for x component.
yeah, sine will be for x component, yeah,
Sine 30. If you want cosine
60.
101.
60, then 60, this will be 60. This
Yeah,
will be
or
60
60,
if you
yes,
want,
yeah.
yeah. So this will be 600 cosine 60 and 600 sine 60. Or if you're using this angle, then this will be 600 cosine 30 and this will be 600 sine 30. So in such problems, simply you have to resolve it in x and y direction and then multiply with their unit vectors. You will get the force vector. So whatever you get here, so your force vector will be simply uh, this is fx, for example, into unit vector in this direction is minus I plus fy, that is this one, into j. Okay, because unit vector in this direction, then it will get, you will get the force vector. So here you see, so f 600 sine 30 and this 600 cosine 30, and unit vector in this direction is minus I and in this direction plus j. So 600 cosine 30 into j, and this is 600 sine 30 into minus I. Then add them together. So and find out the value of 600 sine 30 and 600 cosine 30. You will get this. So this is how you have to convert into force vector, and that's why I'm writing it very important, because many times you require this. So when I ask convert this force into vector, you should be fully comfortable, that without any problem you can convert the force into vector form. Now this is the non-rectangular component example. Here determine the magnitude of the resultant R of the two forces shown below and the angle theta which R makes with the positive. So in this question you have to find out two things. One is R, second is theta. So as you see, these are the two forces acting at a certain angle. So you can use the law of parallelogram to find out the total force. So if this is 7 kilonewton and this is 5 kilonewton, this angle is given 45 degree and this angle is given 15 degree. So draw a line parallel to this, another, and draw a line parallel to this force. Okay. And then the diagonal will represent the resultant. So this will be your vector R, okay, or R. Now this triangle we want to use for finding the R. So this is 45. So as you know, this angle will also be 45 because of the alternate angle. And this is making an angle of 15 degree with the horizontal. So this side will also make the same because this line and this line are parallel. So this will also make 15 degree. So this is 15. This is 45. So the total will become 60 degree. Then you can apply the cosine law. As you remember cosine law, if this is capital C and this is C small. So A and B are known to you. Here it is, this length will represent the 5 kilonewton. This is 7 kilonewton. Okay. Angle, opposite angle is also known to you. That is 60 degree. So you can apply like 7 square plus 5 square minus 2 into 7 into 5 into cos 60. So you will get the value of R. And once you get R, you can again use the same triangle and you can get the this
Doctor,
angle. Yes, please.
the 45 angle, I understand why you put it there, but the 15, why?
You see, the parallel side, whenever you say if this line, this line, this line are parallel, that means if this angle is suppose 20 degree, then all these, if they are parallel, eh, they will make the same angle. You followed? So here this side and this side are parallel. This side and this side are parallel. So if this is making 15 degree with the horizontal, so definitely this will also make the 15 degree with the horizontal. Is it clear now?
Okay, clear.
Okay, yes. So here you see, this is your 7 kilo, this 15. So what I have done, this and this, they are forming a parallelogram. So draw a line parallel to this, draw a line parallel to this, and complete the parallelogram. So this diagonal will represent the resultant. Now this angle is 45 degrees, so this will be also 45. This is 15 degree with the horizontal. This line is parallel to this, so it will also have the same angle 15 degree. Okay. And this is 5 kilonewton, so this line will also represent 5 kilonewton. This is 7 kilonewton. Now we are applying the cosine law here. This is 60, this is R. So c square root a square plus b square is 2b cosine c. That means R equals to the square root of this square plus this square minus 2 times this into cosine of 60. So you will get the value of R as 6.24 kilo Newton. Now you can apply the sine law. That is, suppose this angle is alpha. So sine alpha upon 5 equals to sine 60 over the R. Okay. So from here, R is already known to you. So you will get the sine alpha, that is 0.6995. So from here, you will get alpha, that is alpha equals to sine inverse of this, 43.9 degree. So you got the alpha is 43.9 degree and this is 45 degree. So how much R is making with the x-axis? That will be this plus this. So your
Uh,
theta
uh,
will be
how did
45
I know the sine alpha?
sine alpha by sine law. You see, as per the sine law, suppose this is capital A angle, this is capital C, this is capital B. Opposite to this is small b, opposite this small c, opposite this is small a. So as you know, sine A over A equals to sine B over B equals to sine C over C. So here, because we need to find out total theta. So this is given. So this alpha we have to find out. So we are finding out by sine law. So sine alpha over this length. This length is representing the 5 kilometer equals to sine 60 over R already known to you. So you will get the sine alpha. Is it okay now? You see the lecture number 1. I think this was the last slide.
Yeah,
I
yeah,
took
okay, okay,
I've given
okay.
cosine law and sine law. Okay.
So we know the R. I thought, yeah.
Yeah, you have calculated R. Yeah. So you will get the sine alpha, then you will get the alpha. Once you get alpha, then alpha plus 45, that will be equal to theta. So it is 88.9 degree. Okay. So this is how, by using the cosine law and sine law, we can calculate the inclination of the resultant R with the x-axis. Okay. This problem you can also solve by taking the components in x and y directions. But here we are not recommending this because this topic we will discuss after 2 lectures, I think, in the resultants. So there we will discuss how to use this. But I can explain it here also because you must have studied this in physics. So what we are doing, we are just taking the components in x and y direction. So 7 cosine 45, 7 sine 45. Here it will be 5 cosine 15 and 5 sine 15. Okay. So add the all x components. So T1 cosine 45, and because this direction here will be opposite, so minus T2 cosine 15. Put the values, you'll get this. Similarly, Ry both will be added up. T1 sine 45 plus T2 sine 45, this much. And the resultant will be R is equal to square root of Rx plus R square plus Ry square, you this one. And theta, as you know, tan inverse Ry over Rx. So you will get this. So you can see that R and theta, they are exactly matching with the R and theta which we got here, 6.24 and 88.9 degree. So this is how we can also solve this by taking its components. But at this stage, I recommend you practice the first method, that is by the help of parallelogram, find out the R and then utilize the sine law to get the alpha and then total theta. Because many times in the exams we force you to solve as a non-rectangular components, not as by taking the components in x and y direction and adding them together. So here I complete this lecture. Okay, that is the introduction to the force system.